In this module, we will be looking at various types of acids, including binary and oxyacids. Our objective is to be able to identify different types of acids, as well as to look at periodic trends that determine the relative strengths of those acids. The first thing we want to distinguish between are binary versus oxyacids. Binary acids are those that contain two elements, not necessarily two atoms. We can have acids that have two different elements but have three or more atoms. Oxyacids are those that contain an oxygen atom, and those that form from many of the polyatomic ions that we learned earlier in our chemistry studies. HClO4 is an example. There are many different examples of these oxyacids, including many different options with chlorine and oxygen. We can also have HClO3, HClO2, and HClO. When we look at our binary acids, we see a periodic trend that makes it easy to rank these acids in order of increasing strength or increasing acidity. As I go from the top to the bottom, I see an increase in acidity due to a decrease in the bond strength. Because that bond gets weaker, it is easier for those hydrogens to come off, and therefore we will get more dissociation. So HF is a weak acid. HCl, HBr, and HI are also considered strong acids, but of those three, HI is considered to be the strongest. When I look at the trend from left to right, what I see is that as I go from water to HF, from H2S to HCl, and so on, I see an increase in the electronegativity of my anion. Because of that increase in electronegativity, I also see an increase in the acidity. Because of these two periodic trends, I can generally rank a set of acids in order of increasing or decreasing acid strength. If we look at the bond energies for a few of these binary acids, we see that as we go from HF to HCl to HBr, the bond energy decreases. The bond is getting weaker, and the acid is becoming stronger, because it's easier for the H plus to separate from the anion. When we look at oxyacids, we have two issues to worry about. We have to look at the identity of the element in the oxyacid other than the hydrogen and oxygen. Many times this is actually a halogen, so we're going to focus on those here for our example. The other issue we have to deal with for oxyacids is the number of oxygen. What happens when we look at something like HClO4, HClO3, and so on? And so we have to separate these two issues to determine the relative acid strength. Here I'm looking at HOI, HOBr, and HOCl. What I notice is that as I go from iodine, bromine, to chlorine, my electronegativity is increasing, and when my electronegativity increases, my acid strength also increases. And we can tell this by looking at our Ka values, 10 to the minus 11th, 10 to the minus 9th, and 10 to the minus 8th. The greater the Ka value, the stronger the acid, the more ionization that we will see from our molecule. If I look at a generic molecule, HOX, the increased electronegativity of X will pull electron density towards the X, and therefore shift the electron density of the molecule such that it weakens this bond here, and therefore it will be easier for that hydrogen to be removed. Now we can look at what happens when I increase the number of oxygens. Oxyacids increase strength with the number of oxygens. Perchloric, or HClO4, is one of our 6 strong acids that we've memorized. We know that that is a strong acid, so its Ka value will be much, much greater than 1. When I look at HClO3, we have a Ka value of approximately 1. For HClO2, 1.1 times 10 to the minus 2, and HClO, only 2.9 times 10 to the 8th, a much weaker acid. When we compare these molecules, for example, HOCl versus HClO2, where we have 2 oxygens, we're looking at the strength of the bond between the hydrogen and the oxygen. As we go from HClO to HClO2, the strength of this bond is weakened. It is easier to remove the H+, and therefore we have a stronger acid. Every time we add an additional oxygen into our structure, we see the same trend continuing. So let's summarize what we know about acid strength. For binary acids, those with just two elements, regardless of how many atoms there are, we see increases as we go to the right and down the column. For our oxyanions, we have two trends to look at. We have HOX, where we have the same number of oxygens in each, but the identity of X changes, and that increases with the increasing electronegativity of X. Typically, we're looking at this with the halogens, although we can do it with other elements as well. And then we can look at what happens as we increase the number of oxygen atoms. So we have HAO, where Y is increasing. And as Y gets bigger, our acid strength also increases. So let's look at an example. Which of the following is the strongest acid? Remember, our periodic trend is that for oxyacids, increasing the number of oxygens will increase the acid strength. The hydrogen-oxygen bond gets weaker, and therefore it's easier to remove that hydrogen. Now let's look at another example. Which of the following is the strongest acid? Now we're looking at our trends for binary acids. Remember, when we go down the column, we see increasing acidic strength. Now, remember that we looked at three separate trends. It's very difficult without having quantitative data, such as Ka values, to compare, say, HF and HClO versus some other acid. So when we look at these periodic trends within the acids, we want to look at an analogous group where we have the same general structure, we're just changing one specific property, either the identity of one of the elements or the number of oxygen atoms. Going back to what we looked at earlier in this unit about Bronsted-Lowry acids and bases, we talked about transferring protons, where we have proton donors and proton acceptors behaving as either an acid or a base. Now what we want to look at is a slightly different definitions of acids and bases that applies to different substances, where a proton donor acceptor model doesn't really do a good job of explaining it. And that is the Lewis acid-base theory. So when we look at electron pair transfer instead of proton transfer that we did in the Bronsted-Lowry acids and bases, we have to define what we mean by an acid or a base. Here, for an acid, we mean an electron pair acceptor, compared to our Bronsted-Lowry definition, where we had a proton donor. And for our Lewis base, we have an electron pair donor, whereas in Bronsted-Lowry we had a proton acceptor. So what we want to look at for a electron pair acceptor is some place for those electrons to go. In a base for an electron pair donor, we need to have some lone pair, some unbonded pair of electrons that can actually donate those electrons. Once this transfer has occurred, we have a coordinate covalent bond. Let's look at an example of Lewis acids and bases. Here we have a reaction representing the Lewis acid-base reaction. Note that we have a Lewis base that is going to be acting as an electron pair donor, and a Lewis acid which is going to be acting as an electron pair acceptor. One thing that we look for in a Lewis acid is to look for a hole or some place for those electrons to go. Here we see that aluminum doesn't have any electrons in this fourth spot, and as a result it can accept electrons there, which is what makes it a Lewis acid. If we look at the chlorine atom here, we know that we have 3 lone pairs of electrons around that chlorine that can serve as electron pair donors. Once they react, we form a complex that shows a coordinate covalent bond between the chlorine and the aluminum. This reaction can continue until we get to a Lewis acid, where we have a positively charged species that now can behave as an electron pair acceptor, and a negative species that it can now serve as an electron pair donor. So much in the same way that we talked about conjugate acids and bases with Bronsted-Lowry acids and bases, we see a similar approach here looking at Lewis acids and bases. Let's look at an example. Which of the following could act as a Lewis base? Remember that Lewis bases are electron pair donors. For this question, we need to look at the Lewis structures, which is the same Lewis, but we look at the Lewis structures and what we see is that PCl3 has this non-bonding pair of electrons. If I look at aluminum, note that I have no non-bonding electrons. It has nothing to contribute, so it only can act as a Lewis acid, as an electron pair acceptor. And when I look at AlCl3, I also see this kind of unoccupied space where this can act as an electron pair acceptor, making it a Lewis acid. Now we've completed our unit on acid-base equilibria. There are other issues surrounding this which will be further explored in the unit on aqueous equilibria, which will include titrations, buffers, and solubility equilibria.